asked this the other day. If you have all the variables, can you like know what the volume and the pressure is? Can you figure out what the temperature is of a single gas? And the answer is yes, you can using the ideal gas law. All right, and I'm going to show you how we're going to derive what the constant, how they're all related together here today first. But that's what the ideal gas law does. It relates all those variables that we learned about last chapter, pressure, volume, and temperature, together with the mole into one equation. Okay, that's right. That's right. Pressure, volume, temperature, and moles into one equation. It's supposed to be one big equation. It's actually not that bad. It's actually got fewer variables in the V2, P2, T2, that crazy thing, because there you were having changes in volumes and temperatures and pressures. Yeah. So it actually has fewer variables. Here it is. You ready? You ready for this?
No.
Hurry up.
Just abbreviate it.
Yeah, abbreviate.
What?
Press for pressure.
Right, VTP.
I love the way they abbreviate moles. MOL, like that. One letter, mole. Anyway, ready? All right.
Wait.
Here's the equation. PV equals nRT.
What is N?
What do you think N, and there was two things in there that are unfamiliar for us, N and R. Nert. Nucleuses, yes. How many nuclei we have in there? No. That's why, remember a while ago, you were asking, so just a second ago, somebody said, why don't we use M for moles? Why do we have to write out, why do they actually write out MOL? Well, because M stood for mass, and since M stands for mass, and they write out the whole word moles, they actually use a different letter for moles. When you have a single letter for moles, we use N. It's going to be N. And R is this constant I'm going to actually derive. I know it doesn't make any sense that N will be moles, but it is. All right, so let's go over each of these things, what they are. And they're not as simple as you think. P, you might say, well, okay, obviously P is the pressure. But if we're going to use this equation and the constant R I'm going to give you, I have to have my pressure in atmospheres, or it's not going to work. The constant I'm going to give you will only work if the pressure's in atmospheres, the volume is in liters, the temperature we already know has to be in Kelvin, and as I said a minute ago, is moles. Temperature's always had to be in Kelvin. And this new thing we're going to throw in with all these other gas stuff, moles. That's a great little link to how we can get to quantities like moles and stoichiometry and equations together with gases that we've learned about last chapter. Now, that leaves us with one more thing, the R. Now, let me show you guys. You ever hear of a derivation like for math class? You ever do any derivations in physics for constants? You ever do anything like that? Maybe? All right, well, that's what I'm going to do. I'm going to derive R. Now, some of you drive to school in the morning. I'm going to derive R. Most of you derive a car. I'm going to derive an R. Come on, Marie, come on. Man, all right, that's not that good. Let me show you how I'm going to derive this constant. You ready? Check it out. I'm going to plug in everything I know if I assume 1 mole of a gas at STP. If I assume 1 mole of a gas at STP, I know everything I need in this equation, and I'm going to rearrange it. You don't have to do this, but just watch me do it. Okay, I'll show you where R comes from. If I wanted to solve for R, everybody looking up here, what would I do? I'm going to have to do a lot of algebra in these kind. What would I have to do if I wanted to solve for R? Divide, everybody agree? I would divide both sides by NT. You see it? NT would cancel, and I would get R equals PV over NT. Now, let's plug in everything we know, and therefore we'll be able to derive R. Do I know the pressure of 1 mole of a gas at STP? What's it going to be? In atmospheres.
Some.
Not some, 1. 1 atmosphere. Actually, exactly 1. All right? Don't have to write this down, like I said. I said that several times, actually, Marie, but you're not listening. All right? It'd actually be exactly 1. I shouldn't even have the 1.00. We're going to assume exactly 1. What is the volume of 1 mole of a gas at STP? 22.4 liters. How many moles are in what? That's what N stands for. How many moles are in 1 mole of a gas at STP? 1, exactly 1. And what's the temperature of 1 mole of a gas at STP? 273 Kelvin. So if you plug all of those in, you don't have to do it, I already have it done for you. If you plug all of those guys into your calculator, you're going to get the constant that you're all going to have to know. 0.0821 liter. Now that's fine. You can, all of you can plug that in your calculator and find that. That's the actual number. 0.0821. I think the book may actually use 0.08205, but I think I'm just going to let you memorize 0.0821. What are my units? Well, nothing cancels. Liters don't cancel, atmospheres don't cancel, moles don't cancel, and Kelvin. So your units are liter atmospheres per mole Kelvin. Yeah. Now, that's the first thing I wanted to get across to you, because this is the beginning of your science careers here. You're still early. All you've had is biology. There were no constants in biology to memorize, or to use, or to derive, or do anything with. Okay? Whoops. But something you're going to learn as you get to physics, and you're going to be using more constants in physics, and in Chem 2, and the rest of Chem 1. Whenever you see a constant, it usually has very ugly units. Okay? Because here's what a constant is doing. It's merely showing, everybody watching this now? Mathematically, here's what a constant's job is, Marie. The constant's job is to simply relate together P, V, N, and T. So how they're related together is not going to be a unit that's going to be normal. It's going to be something very strange usually, because it's trying to relate 4 separate things together. And usually the numbers are pretty ugly for a constant. So when you do constants in physics, you haven't done any in physics yet? Spring constants or anything else? No. Well, when you do constants, and when you find some constants in physics, or when you find them in Chem 2, or we're going to find equilibrium constants and rate law constants, they all tend to have very ugly units, such that they don't exist. Like, can you visualize? I can visualize a liter. I can visualize a gram. I can visualize a temperature. Nobody can visualize a liter atmosphere per mole Kelvin. It doesn't exist. It's not a thing. It's just the way that they're all related together. Okay? If that makes sense to you. I don't know. Either way, whether it makes sense or not, that's the derivation of R. Will we ever solve for R again? No, because he's a constant. That's why I told you not to bother to write it down. He's a constant. We're going to use R to get him. So that's, you have to write that down somewhere. You're going to use R to get other guys, but he's never going to change. He's always going to be what he is. Now I'm going to do 2 examples for you on the board here today, and then I'm going to let you guys get started on, well, you'll be able to finish those 2 on your paper, and then there's a couple of other ones to do for homework. Okay? All right, let's do some relatively easy ones here first today. Copy that guy down. These do get harder. I have tomorrow. I'm going to do some. No, I'm sorry. Tomorrow. Well, yeah, I will, because tomorrow the lab won't take the whole both period. No, you only have a single tomorrow, right? Yeah. So tomorrow we won't do this, but I'm going to do some of the harder ones of these. These first 2 I'm going to do today are pretty easy, and they're very similar to the kind you have at the bottom of that worksheet. Now, just like in the last chapter, we needed to write down V1, V2, P1, P2, T1, T2. Otherwise, we got lost with our stuff. Same thing's true here. I need to write down P, V, N, R, and T. If I don't write that down, I'm going to get lost. I'm going to get lost in the unit conversions, the metric conversions, whatever it is I'm trying to convert in here before I even start to rearrange the equation and solve for it. Now, everybody look up there. You know, if this wasn't an honors class, I would be having all kinds of trouble with these variables, because it doesn't specifically say what each thing is. But because you guys are honors, you should be able to tell what the pressure is intuitively by simply looking at the units. Right? Which of all those numbers up there has to be a pressure? 653 torr. See it? All right. What about my volume? It doesn't specifically say the volume is, but we know which one's got to be a volume. Which is it?
Liters.
Yeah, 89.4 liters. It does specifically say the moles, which is 2.89. The R is always going to be 0.0821 liter atmospheres per mole Kelvin. And my temperature must be the unknown, because it says find the temperature. So there it is. Now I write down my equation. PV equals nRT. You know what? Turns out that despite the fact that we've thrown moles into this mix, this equation is a lot easier to deal with than the V2 P2 over T2 equals D1 P1 over T1 for two reasons. It has fewer variables, three reasons. It has fewer variables. I don't have to worry about which one's the first one versus which one's the second one. That's the second reason. And finally, the best reason of all, they're all on the same line. So it makes algebra real easy. What do I got to do to solve for T here? Divide by NR. NR cancels. T equals PV over NR. And watch what happens if you keep your units throughout this mess. P. Uh-oh. What did we not do? Yeah, I got to convert that. What I say about the pressure has to be in atmospheres. So I have to put torr on the bottom, atmospheres on the top. 1 atmosphere is 760 torr. What do I get for that? Do the math for it. If you don't remember to do that, as I'm about to show you with the units, they won't work out. Do the math for that. You're going to get what? What'd you get, Marie?
0.859.
So you got 0.859 atmospheres. Okay, so that goes up here, 0.859 atmospheres. What's my volume? Volume has to be in liters, and it is 89.4 liters. What's my N? Moles. 2.89 moles. And what is my R? 0.0821 liter atmospheres per mole Kelvin. Now, get your calculator out, and let's remind you about something with the calculator again, people. Those of you who are still writing, listen, stop. I cannot do this on the calculator. This times this divided by that times that will give me the wrong answer, unless I use parentheses, right? So your best bet is to go this times this, divided by that, divided by that. Will give you the correct answer. Okay? Okay, do that math for me. What do you get?
324 degrees Kelvin.
324, you said? Anybody else get that? 324 Kelvin? Some more people got it? Okay. I don't know if that's right, but I could tell one thing about the units, whether I set it up right. Watch. Watch what I do. Let's look at these units. Remember what I told you about R. R has these ugly units for a reason. Atmospheres cancel with atmospheres. Liters cancel with liters. Moles cancel with moles, and it leaves you with the only unit left, Kelvin, which is what you'd expect to get for a temperature. Okay? Pretty cool. Kelvin Klein. Okay. Last one. And if we don't finish this, you guys have to leave, you can go, but remember to finish that worksheet, and the homework's over. Oh, I'll put it up there right now while you're copying this down. Okay, now what conversions I had last time, I have different ones this time. Okay, let's take a look what we have to do here. P, V, N, R, T. Watch. Do I know the pressure of this guy? What's the P in this problem? Read it. What number of those is a P? None of them, because it's the unknown. Determine the pressure. Good. What's the volume in this problem? Read. What do you think? 245 milliliters. Good. Can I use 245 milliliters? Has to be in liters. You can show me the work for that, but I'm going to do it quickly. That's going to be 0.245 liters. You should know how to do a metric conversion by now. Uh-oh. I'm not giving moles anywhere. Let's skip him for a second. Do I know what R is? Yeah, it's always the same. 0.0821 liter atmospheres per mole Kelvin. Do I know the T? Do I know what T is? What's the temperature? 45 degrees Celsius, which I can't use. What do I have to do? Add 273 onto that. What do I get? 318. Now let's go back to that N. I don't know, it's not given to me, the moles of the problem. Is there something I can convert to moles in this problem? 25 grams of krypton gas. See it? I can take that 25 grams and I can convert him. Grams at the bottom, moles at the top. 1 mole contains, there's krypton up there, 83.80. I can convert him to moles. Do that for me. And let's see what we get for moles. What did you get for moles, Caitlin? 0.30. Anybody else get that? And that's moles. All right, you guys who have to leave, you can go now because you know what the rest of this is going to be? Just rearranging and solving. So finish that worksheet up and do that homework that's on the board. Copy that down before you go. The rest of us are going to finish this guy up. PV equals nRT. I'm solving for P, so it's even easier to rearrange. I just have to divide both sides by V. So P equals nRT over V, which equals 0.30 moles times 0.0821 liter atmospheres per mole Kelvin times 318 Kelvin over V, which is 0.245 liters. If you don't take that long, you're back before the bell. Try to finish that worksheet at least. At least you guys know what a collector felt probably. Okay, get your calculator out. Plug those in. What do you get for your P? 32. Anybody else get 32? 32 atmospheres. Liters cancel. Kelvin cancels. Moles cancel. Only thing left is atmospheres. Absolutely. All right, you're done. Positively.